Hey guys, today we're going to be talking about astronomy. And the main topic that we're going to be discussing in regards to astronomy is the universe and the Big Bang. After that, we're going to go into the atmosphere and discuss the atmosphere, kind of zoom in on that. So, in my previous videos, my previous discussions with you, we'd already talked about, the planets, the inner planets, outer planets, the sun, Earth, Moon relationships, and also basically the anatomy of the sun. But today, like I said, we're going to jump into the universe and the Big Bang. So let's get started. The first thing I want to talk about is Edwin Hubble. Edwin Hubble was a scientist that basically discovered that there was a Big Bang, that there was actually an origin to the universe, that there was a first start. All right, so what he discovered is that as basically galaxies and stars that move away from Earth, they are exhibiting a red shift in regards to the electromagnetic spectrum. The ones that are coming closer to us are coming towards us. Also, they're catching up, or they're moving at I guess at different rates. They're exhibiting different wavelengths of light, and they would call that the blue shift. Now, the ones that are moving away from us are moving away faster than the ones that are moving towards us. And that would show that basically when you had the initial explosion, the initial energy that was released from the Big Bang, whenever there's an explosion, at the beginning, there's a tremendous amount of energy that would just push that material away. And as the energy dissipates, what's left over at the end moves somewhat slower. Okay, and that can be demonstrated in these pictures right here. So I know that you can see what I see on my screen, and what I'd already previewed some of these pictures, and this is actually Edwin Hubble right there looking through a telescope. Well, there he is right there too. Right here, as objects are moving towards us, they give us a different type of wavelength of light when the ones moving from us typically are redshifted. There's other pictures that exhibit this. See different wavelengths of light depending on where you're looking at or looking towards or from and so forth. All right, so again, the ones that are moving from us, let's pretend this is us right here. If it's moving from us, you're basically going to see a red shift, and if you're moving towards us, you have a blue shift. And that is the take-home message there, basically dealing with an expansion rate of the universe. So let me pull up actually the PowerPoint. So 14 billion years ago is the estimated time based on the size of the universe and how big it is and how, the rate at which these galaxies and planets and stars are expanding from the source that we see. Nothing can go faster than the speed of light. At least that's the current philosophy. They have tried to do this before, to actually make things go faster than the speed of light, but that has failed. That has failed. And yeah, they kind of say that in the news over and over, that they try to prove Einstein wrong, and they'll say, well, Einstein's right again. So Einstein speed of light, and yeah, I'm gonna see if there's anything on news to where why does gravity move at the speed of light? Einstein's theory of general relativity is still valid. 13 billion light years. It's actually 13.7 is the estimated age of the universe. And I just went to Google News and typed in Einstein's speed of light, and you can see that people still talk about it. Okay? All right, now I'm going to go on to the next topic. This is talking about Edwin Hubble and the telescope, and that he discovered that the galaxies that are moving faster than those that are coming closer to us, and the universe is expanding. And this is actually talking about the different laws or different particles that were present at the Big Bang. And you see that really after the initial explosion, you have these fundamental laws already in place, like the law of gravity and the electromagnetic force and the strong force and the weak force. And it's not so important that you know what these forces are. They have to do with the governance of the atom. And these forces or these laws are there to I guess guide the expansion rate or guide the expansion of the universe. All right, when we get here, let me see. It's a singularity event, and what a singularity event means is that there's a couple of different instances, and what's coming to mind, singularity events would be a black hole and the creation of the universe. And what singularity event means is that basically our laws of physics break down. They don't apply. We don't understand it because everything we know basically regarding the universe, it doesn't apply. The laws just kind of like are absent. And there's two scenarios, like I said, a black hole and basically the creation of the universe, or when the universe first came into being. Um, there are different types of black holes. I don't think that's really necessary for us to really go into the different types. Just know that, again, the laws of physics break down at a black hole. It's a singularity event. And basically, black holes reside in the center of every galaxy and kind of keeps everything revolving around it. That's how much gravity it has. It keeps a whole galaxy circling around it. All right. And that's just talking about a supermassive black hole right there. And what goes in doesn't come out. And even the smartest person in the world don't fully understand the dynamics of a black hole. There is something called the horizon event, and that's when our basically laws start to break down. When we get to the horizon event, gravity does slow down time, so time would be very slow there. Time slows down in a black hole. Everything around you would be at a normal speed, be sped up, but as you go into a black hole, everything is going to be like really, really slow. Okay, so like maybe 1 minute near the horizon event of a black hole might equal, let's say, 10 years normally. I don't know. That's just a guess. I don't know. I guess it depends on the type of black hole and the massive gravitational effect that it has. All right, the constellations. Constellations, basically, ancient astronomers used them to navigate. And this is Orion the Hunter right here that we see. And there's two neat things about Orion the Hunter. We have Betelgeuse, the super red giant that's pretty close to us. And we also have other blue stars like blue giants that will eventually become super red giants in the constellation too. I think it's right there, but I forget the name of it. I might have it in another picture in a second. Okay. Anyway, constellations are how the old guys did it. We do it different ways now, basically classifying stars. We classify stars based on luminosity, size, the age, lots of different, the color, the temperature, lots of different things that can give us information about the star and where it fits at in the sequence of events in regards to its life cycle. And the life cycle is typically plotted out by the Hertzsprung-Russell diagram. And the Hertzsprung-Russell diagram is typically just shown or demonstrated or created or made just to show luminosity and temperature. However, it tells us the sequence of stars and basically their life expectancy and what they go through eventually to die and what happens after they die. So it tells us a lot of information, but the main two purposes of the Hertzsprung-Russell diagram is luminosity and temperature. Don't forget that. I've seen that on standardized testing before. Luminosity and temperature. Even though it shows much more, that's the main two purposes of it. All right, let me scroll down here. Again, today we classify stars based on color, temperature, size, and brightness. Okay, talking about brightness, something regarding absolute brightness would be the different name that you might see. It's not called absolute brightness. It could be called absolute magnitude. And absolute magnitude basically tells us the size and actual brightness of that star set from a standard point in space. See, on Earth, we get something called the apparent magnitude or apparent brightness, which may not always be accurate because of the atmosphere. The atmosphere can skew us some and make us think something is brighter and something's bigger and it's closer, but actually it's not. And how we can determine that is basically something called absolute by measuring from a standard distance, absolute magnitude by measuring from a standard distance in space. Thank you for watching. I'll see you soon.